Okay, so today we're going to start the first video in the organic chemistry series. This is going to be a multi-video series exploring concepts in organic chemistry. So yeah, let's get started. So remembering general chemistry, this is chapter 1 in the Paula Uranus Bruce textbook, edition 8. So remembering general chemistry, electronic structure and bonding, section 1.1, intro, and the structure of the atom. So in 1807, there was this guy, Jöns Berzelius. He coined the term organic, so the idea that compounds are derived from carbon and that life goes to life, right? So life can give rise to other life. You need organic compounds to go to organic compounds. There was this central idea that there was a life force, right? It was kind of supernatural in a way. But there was this guy in 1828, his name was Friedrich Wöhler, and he came along and he did this radical thing, and he synthesized from an inorganic compound, right? He took an inorganic compound, ammonium cyanate here. He took ammonium cyanate, and in the presence of heat, he was able to produce urea. He was able to produce urea, which is an organic compound. So he was able to go from inorganic to organic. And that was pretty revolutionary because it was in the face of this concept that you needed life to go to life. So that was a giant leap in in the logic of the time. So moving on into 1.1 further, and this is just review from general chemistry, we know that the structure of the atom here is fairly basic at face value. We have the nucleus, which is a tiny speck in the center of the atom, and it's just surrounded by mainly empty space. And the nucleus is comprised of an agglomeration of neutrons and protons, right? Where the neutrons are neutrally charged and protons are positively charged, and they're held together by the nuclear strong force, right? There's a very strong force there that holds them together. And in the background, in this largely empty space, there's the electron cloud, and you can have electrons that are floating around in prescribed places. These are linear combinations prescribed by quantum mechanics. And we have atomic numbers. Atomic numbers are essentially the identity of your elements. So the type of element you have, carbon, oxygen, whatever. This is going to be linked intrinsically to how many protons you have. So if you change how many protons you have, you're changing your elements. So a long time ago, alchemy, the idea that you could change something into gold, that would be changing how many protons you have. And not only would that require a lot of energy, it wasn't really possible with what they had at the time. Chemical reactions can't really do that. They just change bonds. So not really possible for the Antoine Lavoisiers of the day back then. And mass numbers are just the sum of how many protons and how many neutrons you have. So that brings us into our conversation, of course. Excuse me. That brings us into our conversation of isotopes, right? So the isotopes of an element, that is just a conversation of, they have the same atomic number, but varying mass numbers, right? So different numbers of neutrons. This can bring us into having carbon-12 and carbon-13, and this is how we get radioactive isotopes, right? Because I just said if I have a nucleus here, right? If I have a nucleus and I have protons and neutrons and there's a nuclear strong force holding them together and I add more neutrons in there, well then what will happen is this nuclear strong force that holds them together will no longer be strong enough to hold all of them together. So what will happen is that means you'll have a decay. That nuclear strong force will no longer be able to hold them together and you will start to decay particles. And that is where you get radioactive isotopes. So that's just something to keep in mind there. So we can keep going here, and what kinds of problems could you see in these early sections, right? So in these early sections, you could see problems like this. Number 1, you could see, oxygen 16, oxygen 17, oxygen 18. These are just different isotopes, like I said, right? So what is there to, really know here? Well, they're all going to have the same atomic number, right? The same atomic number. They're going to have the same number of protons, the same identity. They're all oxygen, but they're going to have different numbers of neutrons, So the way you would get this is you would just subtract the atomic number from here, the mass number. And then you'd get how many neutrons are left. Very simple. And then for this over here, this problem, this is a relative abundance problem. How do you get the average atomic weight? So this is the average atomic weight. This is what you would find on the periodic table for chlorine, 35.45 AMU or grams per mole. We have 2 isotopes for chlorine, right? We have chlorine 35 and we have chlorine 37. Chlorine 35 has a relative abundance of 75.77% at 34.969 AMU, whereas chlorine 37 has a relative abundance of 24.23% at 39.966 AMU. So how do we get that average weight, right? Well, you just take that relative abundance and you turn it into a decimal. These decimals here, they add to 1. So whether or not you have 3 isotopes, 4 isotopes, any number of isotopes, their relative abundances would all add to 1. You turn them into decimals, and then you multiply them stepwise into their masses, and then you add all those up as a statistical weighted average all the way into their final mass, and then you should get the mass that's on the periodic table, right? So that's how you would solve these 2 problems. These are very common problems that you would see. These are also more than likely problems that you've already seen in your general chemistry courses. So the next section that we will explore will be section 1.2, the atomic electron distribution. So how electrons are distributed in the atom. I just gave you a very basic run through of electronic structure, but we're going to talk more about how they're structured. So thank you very much. And I hope you guys will stick around and see what else there is to be seen in organic chemistry. Thanks.